Very distinguished guests, ladies and gentlemen, I have the honor on behalf of the Board of Trustees of the Cyprus Institute to introduce the Curien lecture of tonight. It's a very special Curien lecture. May I remind you that the series was started, I think, in 2006, so this will be the 9th episode of the Curien lecture. But this year, it's very special because first, it is the 90th birthday of Herwig Schopper, who has been with the Institute from even before it was born, and who has chaired the Scientific Council and be a member of the Institute and extraordinarily helpful throughout all its life. So we are very glad. And second, because this year the Curien lecture is given by Professor Carlo Rubbia, who doesn't need introduction in science, but I'm still very, very pleased to introduce him. I just realized at the minute that his Nobel Prize in Physics was given 30 years ago, but he looks still very young, so I'm quite happy. He received the Nobel Prize for his contribution to particle physics, to elementary particle physics at CERN, where after inventing or being one of the proponents of a revolutionary concept of intersecting storage rings, he used this machine to discover new particles which were expected, a little bit like the Higgs boson nowadays, but at the time, the new theory, unified theory of electromagnetic and weak nuclear interaction required the existence of particles called W's and Z's, which he found, and of course shared the Nobel Prize with Professor van der Meer, who had built the magnificent machine where this was discovered. So it's a great honor for us to have this Curien lecture tonight. One last word before I give the floor to Minister Dimitriadis. One last word is that to remind you of Hubert Curien. Hubert Curien was the first chairman of the council, of the Board of Trustees of the Institute. He passed away in 2005, and he was not only a very good scientist, but a very respected minister in France, Minister of Science, in a country where it's very hard to be respected if you become a minister. But he succeeded, and I'm glad that the Cyprus Institute has maintained this tradition of having an annual Curien lecture. So before leaving the floor to I would thank Professor Rubbia for accepting to give this lecture today. The next speaker will be Minister Dimitriadis, and I'm glad that he has accepted to introduce. Minister Dimitriadis is in charge of communication and public works, if I understand right. So, Mr. Minister, please.
Well, thank you very much for the introduction, especially regarding the respect part. Dear friends, it is with great pleasure that I accepted your invitation to address the 2014 annual Hubert Curien Memorial Lecture. Today we're very privileged to have here Professor Carlo Rubbia, one of the foremost physicists of the 20th century, delivering a timely lecture about the future of energy. We will hear about Professor Rubbia's decisive contributions to science and technology worldwide in a few moments. It is crystal clear that certain questions regarding the future role of energy in our world need to be addressed. What does the future hold for energy? How can we keep supplying energy to an ever-growing population? What impact will the energy choices we make have on our living conditions and our planet? Why the future is uncertain What's clear is that the world would need a range of energy solutions, including renewable energy resources and other innovative approaches, such as the one that will be presented tonight. The Eastern Mediterranean region is currently undergoing changes to its energy landscape. Recent discoveries of large hydrocarbon resources, particularly natural gas, in the offshore Levant basin, have the potential to alter drastically energy supplies and potential in Cyprus. You know, we have already found some gas in Block 12, and we have Eni doing currently a drill. Hopefully we're going to have the results before the end of the year, and let's hope that they are positive, of course. As there are several issues we're facing that could significantly affect how quickly and how successfully such change will occur, our energy policy includes the implementation of development programs related to the use of energy conservation technologies and the utilization of renewable energy resources. The Cyprus Institute, recognizing the importance of renewable energy resources, and especially solar power, as one of the most promising paths towards sustainable development for EU, Cyprus, and the region, has launched a research division in this fast-growing field, which seeks technological solutions for the exploitation of solar energy, tailor-made for the Cypriot and regional environment. Furthermore, the Institute, in collaboration with the MIT Energy Initiative, is engaged in a joint study on the natural gas discoveries and their implications on the energy policies of Cyprus. And this shows the importance of having such an institute in Cyprus, because we have the opportunity to study all these things here in Cyprus and to apply them how they have an effect on our own market with the discovery of the gas. And the use of solar power. I mean, all the people are always asking, why don't we use more the solar power in Cyprus? We have all the sun, and maybe we should find more efficient ways to use the sun. And I'm glad that in recent years, the government has taken a turn towards using more this kind of energy instead of using other renewable forms of energy, like the wind, for example, which obviously is much more expensive. Research and innovation are key drivers for sustainable growth and prosperity, both in our country and the region. It is internationally recognized that investing in research and technological development, fostering innovation and knowledge transfer, are key parameters towards increasing the competitiveness in a globalized economy. These pillars are, of course, central in our government's program for growth and development. Science and technology are key components for restarting our economy and securing sustainable future operation. Sustainable development based on research and innovation will create jobs and significantly contribute to the social welfare. And of course, this is even more important now that we need to restart our economy. Of course, money is always a constraint, especially in these times. But I think that every penny we spend on research is well spent. In this context, I would like to praise the Institute's contribution in our efforts since its launching. In the few years of its operation, the Institute has succeeded through its research activities and its strategic partners with internationally prominent institutions to be distinguished internationally and to establish itself as a regional center of scientific excellence. It is being developed as a gateway between Europe, the Eastern Mediterranean, and the Middle East, and this is reflected in its innovative research projects, which are focused in addressing important problems that both Cyprus and the wider region are facing. I had the opportunity to visit the Institute, and I was glad that they have some applications that are, they're related to my ministry as well, like the drones, like the Department of Antiquities as well. Lastly, I would like to assure you that both the government and the Ministry of Communications and Works will support the Institute's further endeavors. I'm sure that your future projects will be as successful as the previous ones. Thank you.
Dr. Andreas Pitas, who chairs the executive committee of the Cyprus Institute, will now address.
Although Professor Brezan made a very good introduction. And since we have our birthday man or birthday boy of today here, let me say a few words also about Mr. Hubert Curien and, of course, our guest of honor, Mr. Rubbia. It's really a great pleasure to me to welcome you on this Hubert Curien Memorial Lecture. Tonight's lecture is connected with two scientific giants who have made and continue to make crucial contributions in the last decades for extending the limits of our knowledge. Professor Hubert Curien and Professor Carlo Rubbia, both of them leading personalities in research and education, with work that significantly shaped today's understandings in several scientific fields. This year's lecture is part of our celebrations of Professor Hubert Curien 90th birthday. The Cyprus Institute was so privileged to have Professor Curien's involvement and guidance to his creation and development from the very beginning. He was one of the architects of the Institute, member of the team of international scholars who, along with Ernest Moniz, now with the Obama government Minister of Energy, Guy Ourisson, Frank Rhodes, and Kostas Papanikolas, of course, for 2 years, 2000-2002, labored and with the engagement of tens of international personalities devised the blueprint of what was to become the Cyprus Institute. His role as a founding trustee for 2 consecutive terms and as the chair of its Scientific Advisory Council was pivotal in ensuring the aspired levels of scientific excellence and success. His imprint on the Institute is everywhere. It is very difficult to stop recounting his contributions, but I'm afraid this will not be right. You are here to listen to Professor Rubbia. Tonight, we are also greatly honored to have for this special celebratory lecture Professor Carlo Rubbia as a speaker. Appropriately, the career paths of Curien and Rubbia have crossed on several occasions in the past. Professor Curien served as Director General of CERN from 1981 to 1989. Chopin's years at CERN as Director General saw the construction and installation of the Large Electron-Positron Collider and the first test of 4 detectors for the LEP experiments. Chopin's mandate also saw the awarding of 2 Nobel Prizes in physics to CERN physicists. In 1984 to Carlo Rubbia, today's speaker, and Simon van der Meer for their contributions to the project which led to the discovery of the W and Z particles, and in 1988 to Jack Steinberger, who was a joint recipient of the prize for the discovery of the muon neutrinos. Professor Curien also served as director of the Deutschen Elektronensynchrotron Laboratory in Hamburg, the pride of German science, and the principal force of the leader of the effort to create the wonderful synchrotron facility Sesame, which exemplifies the vision of the leader who is using science for peace. Fittingly, he was the first president of the International Council of Sesame in Jordan. His scientific leadership resulted in remarkable achievements of these laboratories. In more recent years, Professor Curien has dedicated a lot of his time for the establishment of research centers in the Eastern Mediterranean and the Middle East. Today's speaker, Professor Carlo Rubbia, started his work at CERN in 1961 and became its Director General in 1989, succeeding Professor Curien. In 1976, he suggested adapting CERN's superproton synchrotron to collide protons and antiprotons in the same ring, and the world's first antiproton factory was built. The collider started running in 1981, and in early 1983, an international team of more than 100 physicists, headed by Rubbia, detected the intermediate vector bosons. In 1984, he was awarded, as I said before, the Nobel Prize for Physics for this discovery. From 72 to 89, Carlo Rubbia has held the Higgins Professorship of Physics at Harvard. He was the president of Synchrotron Trieste, synchrotron light radiation source, the company in charge of building Elettra, one of the first third-generation synchrotron radiation sources in the world, together with Berkeley and Grenoble. During the 90s, Rubbia proposed the concept of an energy amplifier, a novel and safe way of producing practically unlimited nuclear energy, exploiting present-day accelerator technologies from natural thorium and depleted uranium. The energy resources potentially deriving from this technology, which is actively being studied worldwide, will be practically unlimited and non-proliferating. During his term as president of ENEA, the Italian National Agency for New Technologies, Energy and the Environment, he developed a novel method for concentrating solar power at high temperatures for energy production, known as the Archimedes project, which is presently being developed by industry for commercial use. Since June 2010, he is the scientific director of the Institute for Advanced Sustainability Studies in Potsdam. Professor Rubbia, please accept our most sincere thanks for your presence, and we look forward to your talk. Thank you very much.
Right. Thank you very much for being here. First of all, let me say, Minister, has to leave. Ladies and gentlemen, friends, there are several reasons why I'm here today. I'd like to mention two, which seems to me of great value to me. The first one is the fact that we're all here to celebrate Herwig Schopper's 90th anniversary, which is a very important event, not only for the people here, but also in general, worldwide. The second argument is also that this is a Carlo Curien lecture, and I've been a very good friend with Monsieur Curien all his life, and it seems to me that this is a good opportunity to celebrate him with a presentation of something which I hope you would have certainly enjoyed listening to. Okay, so let me get going with this because my time is up and I have to finish. Let's hope the computer works. Right, we are getting there. Just a moment. As usual, we have a mystery of. There we are. Just a second. Okay, so we're getting there. Is that working? Wait a minute. There's something going on here which is stuck. I hate those computers. I mean, it's really true that when you're doing. In the past, we had these transparencies. Were so nice. You put them on the screen. Let's see. Here you go. That's stuck. Click adding notes. So just to make it.
It's okay.
It's moving. Relax. There we go. Okay, we made it. So this is my present activity. So you can see here, and let me get started. Let me start first of all with talking to you a little bit about climate on the Earth, which seems to me is one of the main arguments for today's discussions. And let me also come with a reconstructed global Earth temperatures over the last 500,000 years, based on the Vostok ice core from Antarctica, which was a French-Russian collaboration. We did this in Petit and Das in 2001, and shows essentially the distribution of the temperature of the Earth over the last 500,000 years. Actually, the data now reach over 1 million years, and you can see the first important thing is the fact that, in fact, probably the man, Homo sapiens, started his lifetime over there. Then the earliest Homo sapiens in Africa occurred about 100,000 years ago. And then the agriculture begins in modern time, which is the present times, about 10,000 years ago. And in fact, the location in which we are now was one of the first places where such a thing has happened. And it has been during the last interglacial period, during the 10,000 years, which has permitted to sustain the development of the human civilization as we understand it today. So we have 10,000 years of human civilization out of 4.3 billion years of Earth statements. And the second remark we can say is that most of this time, over the last 400,000 years, it's so beautifully measured by this Vostok carrot, show to us that the period of modern times, interglacial period, is an exceptional situation. It's exceptional in the sense that it happens only in this very short period of time that we reach the temperature, while otherwise the temperature would have been at least 10 degrees below. And 10 degrees temperature, temperature means that glaciers have covered most of Europe and most of the northern hemisphere and southern hemisphere. So we are really extremely lucky that we had the longest glacial warm period in less than 1,000 years. And the real question, of course, everybody has to ask himself, why did it last only 10,000 years? And will it continue forever, or there will be a moment in which things will come back again? Think about our 7 billion people compared with the fact that suddenly, for the same reason which we saw in the past, the temperature of the Earth may change by 10 centigrades average value. What kind of consequence will that have will be absolutely dramatic. So we're living in a very delicate and complicated world, and this is certainly one of the things we should not be forgotten. Okay, now if we go to a more clearer picture, and we look at the last period of 10,000 years, indicated in this graph, you can see very clearly that the temperature is not constant. The temperature has changed significantly. You can see changes there, which are essentially half a degree of changes in difference is indicated there as a typical example. And there will be a warm period separated with cold periods. And starting, of course, from the fact that during a period of time, for no reason at all, the temperature, not apparent reason at all, the apparent temperature of the Earth was raised over about 10 degrees centigrade to come to the warm region. And now the beginning, of course, of the left represent the end of the last glaciation, which was 11,000 years ago. Warmer periods are indicated there. They occur roughly every 1,000 years. And they are intermixed by period during which the temperature is reduced. And the second important question which has come up here is the effect of associated with the CO2 emissions, which of course is the main question in today's discussion. And you can see that at least historically there's no evident correlation between the CO2 atmospheric concentration and the temperature. Presently, CO2 concentration is grown. Because of the men, it raises from 280 parts per million in volume to 380 parts per million in volume. See the huge change, and this is of course important question: is what are the other consequences, especially based on the temperature changes and so forth. If you go to understand a little better more recent times, there is a very nice work which has been done by Lundquist in 2010, which shows the last 2,000 years of temperatures in the northern hemisphere, which covers Europe, covers Japan, covers in China and Russia and Northern America. And you can see that in fact there are some Earth climate has changed naturally between the cooler and warmer conditions on about 1,000 times. You can see there that it was warmer during the Roman period, the medieval period, and then now we are in today's period, which you have a similar type of situation, and it was colder in between. We have two very important colder periods, dark ages and little ice age, which in fact was quite difficult. This is the reason why several people, Vikings, had to leave many regions of Iceland because of the fact that it was getting really too cold. 1-2 degrees temperature make an enormous difference to the amount of conditions of our Earth and so forth and so on. And then you see that the effect here are measured with much accurate measurements. By the way, the Romans' time were warmer than today, were significantly higher temperatures. For instance, the elephants which have crossed the Alps would not be able to cross the Alps today because the temperature of today is lower than what it was at times in which Romans had to survive the attack from the Punic places. Now, the new phenomena is coming up, of course, everybody knows about it. Let me briefly mention that the permanence of the warm period after the last interglacial period has been essentially to create and sustain life and civilizations are today. And this is an essential survival, the element which for survival that we must preserve at all costs. This is why everybody is concerned, especially young people are very concerned of that. But as well known, we are presently facing a new phenomenon which was coined by Eugene Sturmer and popularized by the Nobel laureate Paul Crutzen, which by the way was the first of your Curien lecturers, I suppose, many years ago. And is called the emergence of the man-made anthropogenic, the word anthropogenic was introduced by him, era. For the first time, human activities may strongly influence the future climate. For instance, since 1750, 1 million tons, 1 million times a million tons, which is 1,000 gigatons of CO2, have been injected into the air, to which may other pollutants have to be added. And the first signs of an anthropogenic era have been already detected. This effect should be curbed to avoid the irreversible effects of major climatic changes. Now, on the other hand, the most evident effect of the presence of men is one of the most important effects is the emissions of CO2. And you can see here as a function of time how the quantity of CO2 emitted in measured gigaton of carbon per year has been occurred from the beginning of the present year until today. You can observe from this curve that in fact there has been a change in slope around the year 2000 coming in because of the rapid growth of the emerging countries, especially China and India. And you can see that the fact is such that we are now growing in the indicated data as quickly as possibly can. They follow the IPCC A1P predictions for a fastest and fully uncurbed emission process. From 6 gigaton per year of carbon in the early 90s, we are nowadays at 9.5 gigaton per year. By 2020, and if we follow the present rate, we'll reach twice the value of 1990, which is 12 gigaton, a factor 2 increase over 30 years. Let me also point out, as you'll see in a minute, the amount of, it's not the rate per year which counts, but a totally integrated amount of CO2 accumulated. And of course, there is not only the CO2 which produces that, there are other phenomena. You can see here the methane is second, nitrous oxide is third, and very halogenated compounds are also there, and they all contribute to produce some significant change in what is the presence of the Earth's atmosphere. Now, the next important question, which I think I would like to ask is, how long will CO2 last in the biosphere? This is a question that not very many people know about, because one thinks it's long, but when you ask how long, you find that many people answer, I don't know. And let me try to explain you what the situation here. Here is an example of how it could be the emissions of CO2 over the subsequent years. You can see that 2100 is just 1 point, and then in the next 200 years, we might be able to emit as many as, let's see whether the thing works like that, as many as of the order of 5,000 picograms of carbon, which is just the total amount of fossil coal which we have available, and that may last a few hundred years, during which we may progressively burn. Even if new technology will exist in some part of the countries, some other developing countries may continue inevitably to burn coal over these years. And the consequence of that is indicated here as atmospheric concentration. You can see that this effect is producing a rise corresponding to the image of that, but then you see that essentially the thing is constant. Is that this is 2,500, it's 500 years from now. You can see in fact that the amount of atmospheric CO2 remains practically constant. This is depending, of course, the values of course depend on how much you have injected in the first place. A mean atmospheric time of the order 10 to the 4 years is in stark contrast with a popular perception of only a few 100,000, several hundred years. Indeed, the mean fossil lifetime of CO2 is about 30-35 kilo years. And this has to be compared, for instance, with the lifetime of plutonium-239, which is the main origin of nuclear power. And this is, as I say today, public perception of nuclear energy. When the public perception will keep telling us that CO2 is also lasts as long as plutonium coming from nuclear power, I suppose some people will have to change slightly their point of view on this subject in one way or the other. Now, this, of course, simplification means that the longevity of a CO2 lifetime This is the paper reference. Now, it can show you, in fact, you see, if you have emitted 5,000 gigaton of carbon, which is roughly what we have burned in terms of coal, over several hundred years, you will observe as a function of time this distribution, which is indicated there. See, the length here is going all the way up to 100,000 years. You can also see in this line here, just see whether I think it works. You can also see this is the pre-industrial level, and you can see that in fact you go well above the pre-industrial level here over a time essentially forever. In fact, the numbers are that after 1,000 years, somewhere between about 1/3 of the fossil carbon is still there. After 10,000 years, about 10 to 15% of carbon is still there. And after 100,000 years, something like 7% of fossil carbon was still present. That means equivalence forever. So our activity of putting CO2 into the atmosphere, it's a permanent change on a longevity which goes far beyond anything we know about in terms of human civilization. We got this CO2, we got to live with it for the rest of our conceptual lifetime to come forward with. Okay, now let me look at the other situation. The second situation is the presence of CO2 will modify the temperature of the Earth. Sorry, you can see here, you can see here, this picture. And this you can see that in fact, as a function of time, we have observed here two things. Here you can see the atmospheric CO2, which has this yearly change and rapidly growing. This yearly change comes from the fact that every year the winter and the summer have different amount of vegetation, so for a different amount of CO2. And you can see here the distributions in the amount of the temperature of the Earth. You can see that after a beginning of, which is relatively constant here in the 70s, the temperatures will be rising all the way up to year 2000. And then around year 2000, at the time in which Pachauri received his Nobel Prize for having discovered that, suddenly the amount of the emission seems to have stopped. And you can see that over the several years until today, while the temperature is remaining essentially flat, the prediction from IPCC, simple, a naive prediction, would have told us a rise like this. Instead, we go to about, the difference is quite substantial. Now, the average temperature emission in the last 17 years shows small temperature drop rather than a significant rise, in contrast with much more naive previous extrapolation. You can see there the expected IPCC, and you can see the observed situation. So what is the cause of that difference? Now, you can also look at it in a more detailed way by expanding the remaining time from the year 1800 here onwards, year 2000 from 2000 to 2014. This is the last 15 years. You can see that is the prediction from the October 2091 to September 2001 prediction from IPCC. Would have given this line like this, but in reality the distribution is like that, and depending how you fit it, whether you fit linearly or the fifth power, you can see the difference between the 2 points is quite substantial. The expected distribution with the errors are there, and the observed distribution there with the errors. So what's going on? That's a really important question. Why we don't see such a rapid increase of the increase in temperature as we had naively expected, say around the year 2000. Now, to see more clearly this situation, you can see the plot over 5 different global estimates, which are indicated there. They're indicated in these particular cases. They all are in perfect agreement with each other. They say to us that the temperature has grown up to the year 2000 to roughly something like 0.4 degrees, 0.3, 0.4 degrees, and then since the last 20 years, the thing has been extraordinarily constant and is valid for all kinds of different models and calculations, which show the fact that this is a real fact. It's not an impression of some estimates of some person or the other. And the difference, of course, is about a little less than 0.4 degrees with respect to 1980, and it stays constant. The other way of looking at it is this graph here. If you just extrapolate from this last period, you can find that no global warming has been observed for 17 years and 5 months. This is the line corresponding to 0 changes in temperature, and here you can see the trend, which is essentially flat in this condition. So we are facing a very strange situation. On one hand, our emissions CO2 have been growing quite rapidly because of the presence of the development of various people. We produce in a few years we will make twice as much CO2 that we produce every year, and it's integrated over tens of thousands of years, so it stays there, and we don't seem to see that. So the question is, what is going on? And the answer is an unstable balance between the CO2 warming and aerosol cooling. You see, the 3 watts per meter squared change should have led to a warming of 2.4 degrees. But the observed warming trend is only 0.75 degrees, namely only 30% of naively expected anthropogenic warming up to the anthropogenic period. So this is a situation which we have to face as a fact. Now, you can see here how we expect the 3 contributions to be there. You can see here the contribution of CO2, CH4, NO2, ozone, and everything's there, and black carbons right there. So these are 3 contributions which are contributing to this famous 3 watt per square meter increase. Now, however, in reality, if you look more carefully, you see that there has been a masking phenomenon there, because about 20%, 0.5 degrees warming, is still stored in the ocean. It will take some time before the ocean comes along. Other 4 masking effects are going in the opposite direction. This is the dust which is produced by aerosol, which are going in the opposite direction, which give you a negative term, 1.2, which is significant with respect to the initial 3 coming from the gases, and then also the question is cooling by land changes about 0.2 watt per meters. So in fact, instead the facts all in agreement, instead of having 265 watt per meter squared, we only get 0.75, because those effects are going to be present today. Now, of course, this effect depends on our use of energy, our use of carbons or fossils, and obviously the lifetime of the CO2 will be infinitely larger in time than the other activities. So as soon as we will clear up the aerosol masking, and soon time the ocean will have learned the increase in temperature and so forth and so on, these numbers will come back and we will be back on the right course. So in fact, the total forcing is this one, but the surface is quite substantial with respect to the net forcing is squared. The surface is indicated there. But then the conclusion is the anthropogenic warm-up is on course, only we don't seem to see it. We believe it's not there. We can go off and can start saying, don't worry about it, we keep going as business as usual. But in reality, this hidden effect is growing up. As soon as we have eliminated these other phenomena, this effect will come up louder and stronger. That will be too late, because it will be too hard at the moment to be able to do anything, because at this moment we will be able to have an irreversible emission from CO2 emissions, but we will not have the corresponding masking effects which are indicated there. Now, let's then work to, this is the general situation from the point of view of the climate. Now, what is the situation when it comes to energy production and industry? Here you can see the primary energy growth, the primary energy growth is International Energy Agency of Paris has given very nice numbers which predict the energy growth in the last 25 years. And indication is there is that the fossil burning will continue unperturbed, as indicated. There you can see there the fractional heat losses for various things. You can see here that, in fact, you can see here that let me go through this graph so you can see better. Small contribution, the renewable will have a small contribution. In fact, you see that here is renewable, which go just slightly longer. Then the natural gas is growing. Nuclear is presumably getting a little lower, and oil is coming down, and coal is coming down a little bit. But this situation is therefore very, very close to what it was before. Now, if you ask yourself where this extra energy is coming from, the answer is pretty obvious. It comes essentially from China and India, which go from 12,000 geocarbon in today to something like, which is about 17 of these same units, and their contribution coming from China and India is 50% of the total. The other, USA, Europe, and other OECD are roughly constant, and of course the other Middle East and Africa are rising significantly together with Latin American countries. So in 2035, we are going to be irreversibly going to very small contribution of renewable, including hydro, and continuation of massive fossil burn. This is the general situation which we have to face today. Now, the question then is, the conclusion therefore is the current worldwide energy supply is based mainly on the availability of fossil fuels, and they will remain indispensable for the minutes to come. The transformation to energies with lower emission and a quantitative significant amount of CO2 are amongst the most important technological challenges of our time. In order to curb environmental changes, it is necessary to proceed simultaneously on 2 parallel lines. One is a more efficient and friendly utilization of fossil fuel, curbing the effects of their anthropogenic emission. And the second, of course, as we have had, is the development and progressive utilization of renewable energy sources. Both activities are therefore, both level the energy production are therefore the only practical way out to this anthropogenic warming threat. And the situation is that you can see that unless something really happens in a significant way, we may be fooled by the risk that in fact we are not doing nothing for another 20 or 30 years, but then by the time we reach the conclusion of the thing, it will be too late for the things forward. Now let me continue my presentation now and describe you what is the situation of European policy. Since we are in Europe, we have to worry about what's happening in Europe. During the last as many 20 years, the energy policy in the European Union is based by two very clear priorities. It's spent for 20 years. The first strategic priority for the European Union has been the one of preventing dangerous climatic changes. This is everyone seems to be convinced of that. The second consideration is based on the assumption the energy prices will rise inexorably as global energy demand rises and resources become scarce, and this will necessarily make renewable energy competitively the winners. The second possibility. Now remember, let me remind you incidentally that today we already see for the first time a drop in the cost of oil, which is going from $100 a barrel to something like $70 or $80 per barrel. So this is certainly not something which is very much in agreement with what has been predicted by this ansatz. The resulting policy, energy policy by 2020 is based on the so-called Europe 2020 climate and energy package, namely 20% reduction of CO2 emission from 1990, 20% of European energy produced from renewables, and then a 20% improvement in UE energy efficiencies. By circa 2040, about 80% of the European primary energy should eventually come from renewables. This is the kind of rule that our government has given to us as an outcome. And in that respect, of course, we have to take a very serious look at renewable energies. You can see here the various alternatives. You see biomass, geothermal, wind, hydropower. This you can see the amount of economic potentials of this system. It's all significantly wide. You can see here that the biomass is concentrated where it's green, that here you have geothermal is in Italy and some of the other countries here. The wind, of course, is most important in the north of Europe. And also some region here in France, and then of course the next one is hydropower, which of course is where the mountains are. And amongst those things, there is one enormous big factor which is working in respect to these numbers, which are relatively small. There is the contribution coming from concentrating solar power, or generally solar power, which you can see here. It's covering the whole of the south of Europe. I mean, your island is right there in the middle of it, and you can see that economic potential there are 600,000 terawatt per year compared to a few thousand terawatts coming from this. And as a comparison, the demand for electric power in Europe plus the desert in 2050 was 7.5 terawatts a year per year, and worldwide will be 35,000. And now here you have 600,000 present in Europe, so you clearly have plenty of possibility. This has to be exploited. Sorry. You can see here from this graph, for instance, this is the size of the world electric power by 2050. The European 25 thing, this is the German size. And here you can see here the Nasser Lake area, which is sitting there, and the Nasser Lake area is equal to the amount of now natural gas. Such a surface equal to natural gas emitted by Saudi Arabia today in terms of oil and natural gas. Could be done by using solar over this small little surface there. Now, of course, the cheapest energy is always the best energy. The next question is, how are we doing with costs? You can see that today the solar is too expensive, but by 2020 it should come down. The wind is already a winning side. You can see here it changes a little bit. And the biomass is also can go from there to there depending on the kind of biomass. But it's quite clear that by something like 2020 or maybe a little earlier, we'll have a parity of this renewable energy with respect to the standard ways of producing electricity. And therefore it is quite clear that the price problem can certainly be solved by some kind of additional consideration. Now, in order to have a better clarification of the situation, let me choose the European energy system based and take the German description as an example of the situation. Greenhouse gas emission is top priority. The goal of German energy policy to reduce emission of at least 40% by 2020, by 80% to 95% by 2050, relative to the level of 1990. You can see here the situation. You can see what's happening. This is the amount of CO2 equivalent produced by Germany in 2090. Now, with the we are here 2010. Most of these reductions coming from the former Eastern Germany elimination of the old systems. But by 2050, we hope to go from here to there, so to get something like 95% of reduction in terms of yield. And this is essentially, this is waste, this is agriculture, this is transport, etc., etc. So you can clearly see that according to that scenario, by 2050 will be totally different, the situation. Let me show you this picture more clearly. You can see in here the photovoltaic. You can see here the various forms of energy, which produces essentially, you can follow that line, you can see it yourself, which produce electricity. Electricity is going then to this is industry, residential, commercial, and transport. And you can see that essentially electricity produced mostly by wind is then used to produce also during the high power time hydrogen, and the hydrogen then is used to create transport. So the cars will run on electricity coming from the wind, which then will become hydrogen, and the hydrogen will become the main source of transport, will also go to industry in this particular way, as you can see there. In fact, and there will be also heat constructions, which will also come down and contribute similarly. This is heat coming from the sun, and which will also do the same thing. Hydrogen electricity produced by PV, hydro, and wind, geothermal, and solar are the main energy sources for industry and the transport. And the solar is essentially, and the elimination from fossils is gone. So this is the kind of presentation that you see is behind what it is normally believed to be a credible solution from this particular case, which is a little bit in the frame with the situation of European situation. So let me very quickly show you a little better how things are. Now, obviously, the line, in line with the commitment of the member states by 2020 and beyond, wind energy should indeed become most prominent renewable source to be used in Europe to contribute to green gas emission abatement. You can see here where the wind is. You can see that, let me remind you that the speed to the cube power is the energy transported. So this is the major energy consumption is coming from a region out of the coast. This is England, so you see is the North Sea. You have another interesting place down here in France, and maybe other activities could occur in the region down there. And of course, the key is to build very large systems offshore. You can see here 6 megawatts power, and some of these things are going to something like 700 meters deep in the water of the ocean. You can see here the map of the Northern Sea, and you can see from this graph here the situation. You can see that there are 3 types of distribution here. The red are the one operating. You can see a few points which are operating now. The second line is on the constructions, and you can see the white one, which are planned, which will cover all this huge operation offshore of energy with electricity, which will be main source of electricity for Europe in the years to come. Now, of course, let me underline one fundamental difficulty: wind, which is certainly mentioned here. The wind variability in Germany, percent electric demand delivered by the wind turbines energy during the 2007. You can see that sometimes you have too little energy, sometimes you have much too much energy because of the cube of the energy effect, cube of the speed effect, and therefore you can see that when you have too much energy, you can use it to produce hydrogen, and with the hydrogen you can produce transport. When you have too little energy, of course, you have to survive with whatever you have and give you the system. In fact, the average over the year, the wind power delivered is only 18% of the installed capacity. Now, this situation will also imply a new situation with the electricity system. See, this is the present electricity system of Germany. And here you can see the electricity system as is expected when the needs of abandoning nuclear power, or reducing, essentially driving mostly on wind as an alternative source. You can see there are in here several main lines which go from the north area where the source of energy is down to the rest of the country. You can see these new lines have to be constructed. These are 6 gigawatt and up to 12 gigawatt lines which will have to be built to transport over the about 1,000 kilometer distance the energy from the Northern Sea down to the place where people are. And this is, of course, is important difference because essentially now the question is, how do you do this? We are developing something which I very quickly I would like to mention. There is new choice for long power line, which is based on a new superconducting material, magnesium diboride, which is superconducting up to 40 Kelvin. So therefore it can be at high energy, which can be manufactured very simply. And we have a major activity going on in help also with some Italian company to produce magnesium and boron, which are both very cheap materials. With a simple in situ powder and tube, you can combine the two things, and you can produce out of this a wire cable, which you can have to filling for a drawing and cold rolling, an extremely simple method of producing cheap chemical drawing wire in analogy to the niobium titanium. And the wire length today is up to 20 kilometers in a single piece, easily scalable by increasing the length. And the conductor cost is very cheap. It's about €1.5 per kiloamp meter, and in 3 years it will be 0.5 kiloamps. So it's a very cheap and abundant system. And we have developed a program, together with CERN, to build a practical method to demonstrate feasibility of this magnesium boride power line. You can see here a 20 meters long cable carrying a cryogenic cable, in which we have a current in there, which is represented by the following graph. You can see here we have something like 20 kiloamps of current carrying in a wire at up to a temperature which could go up to 40 Kelvin. And you can see that this is being tested, and this test has been successful and is giving us a possibility of constructing very small lines, which of course resolve a very major problem, which is a question of these very huge power lines require overhead power lines, require very large structure, while the transport through this tube with a superconducting power line will be only a very narrow tube. You can see here the drawing of this. This is how it will work. You have a cable riding into, this is the inner tube and outer tube. This is liquid hydrogen or liquid helium or gas helium coolant. And you can see here the two lines which carry 20,000 amps are these very narrow lines here. This whole thing is a tube which is 33 centimeter diameter with a pressure 20 bar. And in fact, you can have to be compared to the natural gas pipeline for the same energy but thermal, which will be 90 centimeter with 100 bars. So it's much simpler to do than the other system. And you can see also here the cryo cooler, which is required to cool the system, is only required only every 300 kilometers of distance. This is something we are developing. The construction of this system will be extremely simple. These are the tubes, diameters which is required. They will be located underground, and then of course it will be covered up, and there will be essentially possibility to transport gigawatts of power in this particular way. In fact, you can see here how the thing is going. Now you see here a 5 gigawatt, which means 5 gigawatt means 5 nuclear powers. For a relative size of equal store energy between gasoline and methanols. And here this is a standard oil and standard material, gasoline, methanol, compressed CH4, liquid hydrogen, compressed hydrogen, and major thermal storage by using essentially a coolant which is used at 500 degrees centigrade, as you are doing, to produce this volume. See, the volume is quite acceptable, and there are no pressure here, no flame in there, and this is for a much important advantage when it comes to the solution. Compared to hydrothermal storage efficiency, unit mass is equivalent to a gravitational water drop of 72 kilometers. Here is a picture of, as I was saying to you, one possible alternatives in which you could carry up into the Northern Europe various solution of alternatives here. And the important question is that all these distances are very long. There's several thousand kilometers, and therefore new technology have to be developed. Now, okay, now let me come back to another question then, an alternative. If Europe is concentrating fully into developing renewable energies in order to eliminate the question of fossils by reasonable time, 2050 seems to be a number, this situation is in total contrast with alternative in the US. And this is represented by the so-called shale revolution, which is indicated here. This is a paper coming from Time magazine showing this rock could power the world. This was started already in the 60s and the 70s, and it was predicted by year 2000 there would be a commercial extraction oil from shales. And it turns out that the proven reserve of this bunch of fossil fuels alone can provide both energy requirement for about 100 years. Only 1/5 of the estimated potential resources could provide more than 200 years of projected energy needs. So the other important alternative go to unconventional forms of natural gas resources. And this is explained very clearly here. Is a fossil fuel with the highest decarbonization. And natural gas represents the practical alternative to the presently growing explosion for source of energy. Of course, there are many other required, and this new development with precursor indication, new remarkable era abundant cheap energy production for fossils. This is what it's been advertised, but novel metal must be produced in order to ensure at the same time more substantial reduction on the green gas emissions, because even if CO2 is a factor 2 times less than coal, certainly there is a huge the CO2 problem persists very seriously. What are these two technologies that are being proposed? There are two of them. One of them is shales. You see what happens here. Sedimentary rock formed from deposits of mud, slitted clay, organic matter. You do hydraulic fracturing of this stuff, involve pumping of water mixed with chemicals, high pressure into a well, which has been drilled. The fluid creates fractures in the rock in order to get the gas out. So you go in there, you fracture this material at a very big depth, several thousand meters of depth, and the methane actually comes out, and you collect the shale gas as a gas out of the system. The second method, which also being considered, is called coal bed methane. The coal bed methane is another method which is absorbed. Coal is absorbed in a solid matrix. A release of coal seam is depressurized. Methane is extracted by drilling wells into the coal seam. The water pressure is decreased by pumping water from the well. You have water coming down here. The water is coming into the system. It creates develop the wood well, and the decreasing pressure allows the methane to dissolve from the coal and flow as a gas up to the well of the surface. So the gas comes out as a methane pipeline through this system, using the water to modify the situation of the coal and to extract the methane out of the material, the coal bed. Now, this has done a lot of interesting results. You can see here the gas consumptions. You can see that this revolution, shale revolution developed by the Americans, has created a new facts of life. You can see here that until 2007, 2008, before the development of this technology, the cost in Europe, in Japan and US of natural gas were roughly the same. But then after the shale gas was developed, the US is coming down. The bottom price was a moment here in 2011 when it reached about $2 for a million BTU, while the situation in Europe was 11.42. Now, of course, Japan is much higher because Japan is using essentially liquefied natural gas. So the difference between these two is that the liquefaction is necessary in Japan, while Europe can get more gas out of direct pipelines. And I mean, the difference in natural gas price in the US with respect to Europe are, as well known even today, quite remarkable. There's a big difference in the cost, which has to be faced and understood. Now, the consequence of that is the one that the situation is the coal emissions have been reducing themselves very rapidly in the United States, because coal is more expensive than natural gas, and the gas has been growing. And in April 2012, there was a moment in which the same quantity of energy was produced between gas and coal, even in the US, and now the situation is indicated there. You can see the clear phenomenon. There's an important shift of electricity production from coal to natural gas, and you can see here the consequence into the primary energy distribution. You can see primary energy production in Europe, while Europe is being reducing the primary energy production for various difficulties, including also the crisis, economical crisis. In North America, the development of shale gas has really made a real explosion. And you can see how quickly the million of tons of oil equivalent produced in America have been growing compared to the falling situation in Europe. The other important question is the abatement of CO2. You can see here that the US is the only major country which meets the Kyoto prescription in CO2 emissions. While the amount of energy has been growing, the fraction of CO2 emissions is roughly back in 2012, was roughly back at the level of 1990. And this is coming from a replacement of natural gas with the other system. Now, also oil production has been developing here. You can see here the effect of the American shale revolution on the annual gas production in Texas. And you can see the Texas production has been slowly coming down and dying off. And then after the shale production, Carpe Diem, the American shale revolution is really exploding. You can see here how quickly the new production of oil has been produced by this system. And you can see that from this graph here. Here we are comparing three possible situations for petroleum production. One of them is Europe, Central America, and South America, which is slowly decreasing. The Saudi Arabia is here, and the US is there. You can see that after the 2010 shale revolution, now the production of oil in America is bigger than the production of oil in Saudi Arabia. And this new extra production of oil is, of course, one of the reasons why the cost of oil now is going from $100 per barrel to something like $70 to $80 per barrel because of the added production coming from this system. And there's no doubt that US will try to shoot for energy independence in something like 20 or 30 years by going with this trend. Of course, the real question is the methane emissions. And this is a statement which indicates that the natural gas is contributing to a significant but not a very large fraction of the total methane emission. You can see that the natural gas is in fact still less than everything else in terms of all the other contribution to methane, which of course becomes CO2 equivalent is value. Now, then you can see now, I have another 10 minutes to finish here. What are the world shale resources? I indicated in this graph here. You can see that they are global and massive. There are a lot of shale gas in the States, a lot of shale gas also in South Latin America, and they are in China. And in Russia, we don't know what they are. We don't know what they are also in Italy because nobody's looked at them. But you can see that in the rest of the place, there are similar places where shale gas is abundant. The second alternative is coal bed reserves. Again, you can see there that they are also rather flat distributed over the various countries. There are some of them in Europe, some of them in China, in Russia, and Australia. So both resources, CBN resources and shale resources, are very abundant. Now, coming back to European resources, you can see from this graph what the situation is. Poland and France have a very large amount of shale gas. Then Norway is following. Germany is not particularly favorable, but you can see that in fact some of the countries we don't know anything about. For Italy we don't know, in Turkey we don't know, in Spain we know very little of it. But clearly the situation is that if you wanted to go shale gas, you have plenty of sources also within the European system, as you can see, especially Poland and France and Norway are the winners in this particular situation. Now, what is the situation price-wise? Let me talk there. First of all, natural gas situation is indicated here. Natural gas for European industry are more than 3 times higher than the US. You can see here the US contraction natural gas. You see Germany, France, Netherlands, United Kingdom, over Europe. Similar situation are to do with electricity. Electricity produced in industry, notice that a big factor of electricity is coming from coal, is again in the United States more than a factor 2 cheaper than what it is in any one of the European countries. The question of this difference in prices is certainly very considerable. Most important situation is also the chemical industry. You can see here the chemical industry, how they developed in function of time. The chemical European prices are 4 times higher than US. These are ethane. You can see ethane, because of the shale gas revolution, is coming down, is reducing itself, which was similar to this thing, has gone down to this value, while the European value is growing, and you can see clearly that there is a substantial difference, and that as a consequence that you get a very major surplus in the production of chemical products. For instance, the net exporter of US was 800 million in 2012, 2.7 billion in 2013, and is projected to be 46 billion by 2020 by using this big difference between the situation of various chemicals in the US when compared to the situation in the United States. Now, that of course is creating interest into the other countries. Here is the picture of China. China is getting very busy in trying to recover shale gas, and supply, there is enough for that to get 200 years the current level, and you can see how quickly the demand of shale gas production is foreseen in the years to come. So it's quite clear that China is getting very heavy on this. Let me also show to you that this production from China is essentially driven by America. You can see all the most important companies, PetroChina, Shell, Chevron, and the others, which are indicated in this graph, which are companies exploring the shale gas. So the shale gas now in China is essentially produced by American companies, which are occupying this space and the interest in these things. Various places you can see are present in this situation. Now, if we come to the chemical boom, again, this is another question which you have to be very concerned about. There are two curves here. One curve represents the production cost in 2005. Here is the United States, Asia, Western Europe and China, and Middle East, which was very low. And you see the situation now. You can see here the Western Europe is going up because of increased cost of systems. China is there. Middle East, United States have now reached the same production cost as Middle East because of the possibility of the system. You can see here the situation. Here you can see the renewed US competitiveness is now low-cost producers against the shale gas. For instance, US ethylene production costs 1/3 of those in Europe. You can see that, for instance, Western Europe between 2005 and 2012, the cost of ethylene as a chemical product has gone up. In China, it's also going up, but the United States is coming down, is bottoming at the best level possible for the Middle East. And that makes a tremendous difference when it comes to the questions. Now, let me spend a few more minutes, if I may, in clarifying a few questions, and then we have to finish. I've been talking 50 minutes. I'll take another 6 or 7 minutes before I finish. In order to economically harvest this immense energy wealth, it's essential that the effect of progress global warming are kept under control. Now, of course, many questions are there. Natural gas should be kept under control. But, of course, this solution is still one problem we don't have in Europe. Ordinary combustion natural gas is inevitably emitting CO2, although roughly the half compared. And this is producing another program on which I am personally involved, which is the one of eliminating completely the CO2 production associated with methane by transforming methane by not burning methane, but transforming methane into hydrogen and black carbon. And black carbon is solid, therefore it can be separated out, while hydrogen is producing to the system very easily, essentially water. And this process under active investigation by us at ES with the Carlo Institute of Technology, and it sounds to us as a very powerful solution which can be used in order to eliminate completely, in the case of natural gas, the production of energy coming from carbon. The production from hydrogen is 80% of the total energy, 20% is carbon, so you lose 20% of the energy, but look at the advantage, you get zero CO2, and if you don't have CO2, you can keep going producing the natural gas as long as you want, because natural gas eliminating the black carbon is simply hydrogen, which means water. Now here is the difference between the two systems. You can see here the standard reforming, which is indicated there, and the spontaneous pyrolysis, on which we are working on, in which we are producing carbon plus hydrogen. You can see the big numbers are indicated down here. First of all, emissions is 43% here and 0% there. The energy efficiency for a realistic system is 60% here and 58% there, but here the energy is lost or put into and while here the energy is stored. And of course, the problem is the real question is that while this is well developed, this other one needs development, but this is certainly something which, if done in this way, could allow us to continue using fossils and conditions are different. Let me also point out to you very briefly, this is how the carbon structure look like. This is carbon fibers which are produced by such a system. They are very pure fibers, by the way. This is also a very useful compound because Maserati and Ferrari are producing a lot of that to produce cars and other things. Now, that has brought in another question, which is represented by the fact that today, with the present day situation, is that the cost of CO2 is really dropping extremely low. 1 ton of CO2 today costs about $4 for a euro. And this has been collapsed because of a large amount of use of CO2 and then no need to do anything. So here we have proposed to do an alternative. If we make the methane decomposer in which a natural gas becomes black carbon plus hydrogen, it would be worthwhile for us to combine it with CO2 coming from some process and recover the CO2, becomes from a liability becomes an asset, and combining CO2, which is already produced, with hydrogen produced by this system, you can produce methanol. And methanol is a perfectly good equivalent to cars running. In fact, you can produce methanol can be transported like oil, and it can be used to produce all kinds of different activities. And in particular, it is possible for some centralized electricity production to recover again the CO2. So go in a closed loop with the CO2, use once, and then use this system to produce the energy. This is the kind of thing on which we're also working on, which seems to be quite interesting. So in a few more minutes I got left, let me talk about one more question and I finish. Clathrates. Very few people know what the clathrates are. But clathrates is a large untapped reserve of natural gas on the crust. You can see how they look like. This is a clathrate material, which you see there. Is methane hydrate is the most abundant natural form of clathrate, unique class of chemical substances which molecules one material, in this case water, form an open lattice that encloses without chemical bonding and preferably sized molecules of another material, in this case methane. And while stable at temperature of about 0 degrees, higher pressure methane remains stable up to 18 degrees. 1 liter of methane clathrate solid will contain 168 liters of methane, which therefore there is more methane in a clathrate than is liquid methane. Liquid methane is less dense than clathrate. It's a huge amount of material which is perfectly stable. It's called also burning ice. This is something which is well understood and developed. Let me show you how it is. The subject appeared purely academic until recently, when physicists realized that given the ubiquity of both of methane, the common byproduct of bacteria break down organic matter and water in nature, methane hydrate could be present in vast quantities in any environment with suitable pressures and temperatures. Methane clathrates are common constituents of the shallow marine geosphere, and they occur both in deep sedimentary structures and outcrops of the ocean floor. The potential amount of methane in natural gas is enormous, with current estimates covering around the conservative value of 10,000 gigatons. Let me tell you that the amount of natural gas is 200 gigatons, oil is 200 gigatons, and shale gas is about 200 gigatons, coal is 5,000 gigatons, the methane is at least 10,000. As you can see here, the comparison total estimate of conventional natural gas oil is only a few hundred megagigaton. Now, U.S. Information Administration estimates that methane contains more carbon than all the other fossil fuels combined. Methane had larger reserve of hydrocarbon in planetary crust. Certainly consider U.S. territory could supply U.S. natural gas need for more than 1,000 years. And here you can see how you do it. This is the clathrate are in the bottom of the ocean. They are collected in the bottom of the ocean. You extract this clathrate in there, and then you put them with a tube onto the boat, and the boat carries the gas eventually out of the system. See how you can, this is the kind of scenario that you can consider to be a possible scenario. Let me repeat those numbers: 200 gigaton for oil, 5,000 gigaton for coal, and 12,000 gigaton at least for clathrates. So let me show you here a reservoir methane located over between 2,000 meters on the solid surface and observed by large number of locations are major interest in the resources. You can see here all the places in which people have discovered the presence of clathrates. And you can see they are almost everywhere. I mean, of course, we only go near the coasts, but you can see that almost any part of these oceans, wherever you look for, you find either recovered or inferred gas occurrences. So the presence of this huge amount of clathrate is real. It's a fact that you can observe, and it's enough for 1,000 years of use of the system. If you couple it with a solution, as I said, of being able to eliminate the CO2 emissions by using black carbon, it will solve the problem in a very elegant way. Now, conclusion, the last transparency. One best available solution to meet the rise in demands of energy lies in the ability to economically develop unconventional gas resources, which initially can be coal bed methane or shale gas, and in foreseeable future can be methane hydride. North America, India, China, Africa, and Latin America will all have access to cheap and abundant shale gas and oil. Both environmental sensitivities and gas consumption on the rise. The main question is how to recover these huge novel natural gas resources available for millennia to come and economically harvest this immense energy wealth in the most efficient and effective manner and with a minimal environmental footprint. In my view, it's my own view, a revolutionary but unexploited option for Europe are both natural gas going to black carbon plus hydrogen with zero CO2 emission and clathrates from the sea. The clathrates from the sea are much easier to observe than going underground look for shale gas, which is possible in places like America, but it's very difficult in very dense places like Europe. While going to under the water of the ocean and go and pick up their stuff, it's something which is much easier to do. So conclusion is very simple. Europe Union has to decide between cheap and expensive energy. And this is essentially the problem that we have ahead of us. And let me also conclude with a little picture here. You can see here the thing I'm starting to get concerned about global warming. And I finish that. Thank you very much.